Swayam Prabha. Digital India. Educated India.
So, okay, let's look at the demo here. So I will go to demo here. All right, so the first one I'll be dealing with is the mixed precision. So for mixed precision, you have to use TensorFlow version, because I'll be dealing with TensorFlow first, TensorFlow version 2. So I've pulled mine. So this is the TensorFlow. This is 21.12 TF2. This TF2 shows that it is version 2. So I will be running that because I'm running my workstation. So I'm just using, okay. Okay. So I'm gonna connect here. You may not have to go through all this process if you have your TensorFlow on your workstation or on your laptop, maybe via Conda or virtual environment. It's because I'm using a container. That's why I'm going through this process. Okay, so yeah, I have localhost for me. Okay, so I'll be dealing with version 2 first of all. So this is just I just put this together, adapted from TensorFlow website. I hope you can see my screen.
Yes, Tosin, we can see the Jupyter Notebook.
Okay, thank you very much. So I just pick a simple example to do it so that we can actually understand very well. Then on our own, we can later on do complex example because of our time. So the first thing here is that we import TensorFlow, and then from TensorFlow we get our Keras, and then we import the layers we want to use here. Then from TensorFlow Keras, we import the mixed precision. Now, please note what we are trying to do here, achieve here, is using mixed precision. It is not the automatic mixed precision. Mixed precision and automatic mixed precision are the same thing. So the difference is that automatic mixed precision, you don't need to do some manual job. You just, with one line or two, everything is set, it's done for you. But with with mixed precision, you have to do some level of manual stuff yourself. So we're dealing with mixed precision here because mixed precision only is possible with TensorFlow version 2. So let me comment this one out first. So the first thing you do is that because we're dealing with mixed precision, we need to work with float 16, FP16. So you have to use your mixed precision library that we've imported here, the class. Then you call this method policy. So we set policy for our mixed precision. That is, you use mixed of float 16. So when you set that into the policy, then you can take your you make your mixed precision, set global policy, then you put the policy in there. So when you put the policy in there, you need to confirm if it is actually set. So for us to confirm, we need to get the policy.compute type. What is the type is going to use for computation, and also policy.variable type, that is, what is the variable type? Remember, mixed precision is the use of FP16 and FP32. So we run this notes book here. So let's see what happened. Oh, good. So it's showing us that you can see this is a version that is what TensorFlow version 2. Then it says TensorFlow mixed precision compatibility checked. That is mixed precision. That is, it is okay. It is compatible. We can use. Also, your GPU will likely to run quickly with this policy of mixed float 16. Also, if the compatibility is at least, that is, your compute capacity must be at least 7.0, which I've told you before. show you how do you know. If you go to Wikipedia, you can see from here that from VOTA, this is where we have 7.0. Pascal here is lesser than the compute capability. This is compute capability here, the first column. So you can see for Pascal is less than that. Then from VOTA, you can at least, if your GPU is between these 7.5, the storing here, if you're using GeForce RTX 280 and all the lights. So you can check the architecture of your GPU here. So we can proceed from there. So we know that. So the next thing we do is that we want to work with MNIST, which is like the LO word for training, which will make things simpler for us. So we create our input here. So the shape of the input is just 784. And then we check here if we have a GPU on this machine. So if this GPU on this machine, we want to set our layers number of units to 4096. And if it is not, we reduce it to the size of 64. So these are we're creating two dense layer here. So I can run this two dense layer and see that, okay, it has to detect that it has a GPU, which is running, and we're going to use this unit. Yeah, this is the same as putting 4096 is the same as writing it raw directly. Yeah. And then we want to be sure that, okay, each of the dense layer, what policy are they using? Is the dense layer, is it using the F16, FP16 policy, and is the kernel on FP32? So we need to check that because mixed precision is the use of FP16 and FP32. So we check that again, so we can see saying yes, the policy is mixed F floats 16, which word the type is what float 16, and our kernel is what float 32. So we are on the right track here. So the next one here is what to do after the two layer. Then we get our last layer, dense layer, which is where we supply the softmax here. So and we check that this is float 16. So the rule here is that when you are dealing with what the softmax, it has to be because you are about to move into doing your calculating your loss and gradient descent. So it has to be float 32 there in order to escape the dynamic range limitation that FP16 has. So in order to do that is that we will separate what we have here. We'll separate this layer into what just the dense layer and then separate the activation layer from it. So that is what we have done here. If you look at this line here, we'll just have the dense layer here, and the second one, the output will be just the layer of activation function. And how do we do that? Because we are using FP16 policy, so we need to write this out to cast it back to FP32 here. So we are only casting back the softmax layer only. So now we're good to go. So this is just the exception that we have there. And then, so you can also do that using this line. Of course, you haven't linear here, it can also cast it back with that. So what we need to do next is to instantiate our model. We have the input into the model, we have the output into the model, and then we can pile our model by setting the loss, and also the optimizer set here, and our metrics is what for calculate the accuracy. Then we get here, what we do here is to get our data, the MNIST data. You get your MNIST data, the training will be what 60,000, and the test will be 10,000 as well. So it's downloading, we download that. So after downloading that, so the next thing to do is to initialize our weights. So we initialize the weights here. After we initialize the weights, then we have to do and train the model here. So we can see the model here. So what I want you to notice here is that this is we just put it under 5-air porch so that it will not waste time. So if you can see the time it takes for for each steps, you can see the first one is the first step is where it takes longer, which is 1 second, 6. The others are just 0 seconds, 0 seconds, 0 seconds. 1 second is that it is doing the casting here. This is the first air porch. So at the subsequent air porch, it becomes more faster there. So let's see if this were to be trained without using mixed precision. So if we are not using mixed precision, so what do? If we change from mixed precision to maybe we want to use FP32. So I can just come here and say, like, let me the kernel first, clear the output just to show us the difference, because this is very important. We have limited time. Okay, I've cleared that. So what I will do is what this mixed precision policy, I erase it, then I just turn it back to floating point 32. So this is without using mixed precision here, without using mixed precision. So if you compute here, so what we will see is that you see the compute type is no longer FP16, it's FP32. The variable type is FP32. So let me quickly run all of these. All of this which I've run before. I'm only interested in the results. So everything is FP32. Since it's FP32, I don't need to run that one again to convert. So yeah. So let's run this. So now what I want us to see here is that if you look at this, we have at the initial is 1 second. Subsequent epoch is also 1 second. 1 second 94, 1 second 94. You can see that the time it takes when it is not mixed precision is higher than when it is mixed precision. It might look small, is because we're dealing with smaller data and smaller model size here. That's why. So it's just to show you the differences that are there. When it was mixed precision FP16, you can see we only have one here, and the other subsequent epoch just only took 0 seconds. So I will change it back because I need to show us, in case you are now, the way you write your code, you are using custom loop within your code. So if you use custom loop within your code, then how do you use mixed precision when you use custom loop? So when you use custom loop, then I will show you that one in a GV. Sorry, I don't want to mix things up. That's why I keep now. So we set back to our mixed precision here. So I can run this now back, run this. Okay. 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 Run that then. So look at it when we're back. It's only the first step that we have 1 second, and the others are just 0, 0 there. So when now we want to deal with what loss scaling here. So loss scaling, you need to compute the loss scaling when you are using custom training loops. Here we don't need to compute that. For when we are not using custom loop, it will be done automatically by itself. But in this case, when you use custom loop here, you need to specify mixed precision loss scaling optimized. This is the scaling we're talking about. So when you try to use custom loop, you must specify the scaling optimizer. So you get your optimizer here. This is our optimizer. That's the optimizer root mean square pops. So we use the mixed precision loss scale optimizer to wrap it. After we wrap it through that, we get our loss object here using the cross entropy. Then we get our data again here. So let me run this, get our data. Then so we want to compute the training step. So in the training step here, we get our gradient tape. This is the gradient tape. Under the gradient tape, so what happened? Get your prediction. This is the model. Supply the input X into it. This is a function. We're just writing this function graph from. Then we compute our loss using this loss object. We have calculated the loss object here. So we call it, it takes this value. Then we scale our loss with what we have been talking about before. So this optimizer from the mixed precision local scale optimizer, we use it to scale. So we get the scale loss here. After we get the scale loss, then we also get the scale gradient as well. The scale gradient, using tape.scale gradient, add your scale loss and the model variable that are trainable into it. Then after we have gone that scale gradient, then we get our regradient. So what happened after you have scaled your gradient, then you unscale back. So our optimizer dot unscale the gradient back. So we unscale the gradient back, then we can now use our optimizer to apply to our normal trainable gradient. So we return the loss here. So as we done that, we need to do also for testing, but our testing, we don't need to go through this. So we just write the model testing this way that you see. Sorry about this. For now, don't want to include this here. And here also, I don't want to include this here. So this RTF function is showing, this is a graph format of writing your model. So then, okay, let me run this as well. If I run the first one, yeah, we'll run that. So we run this cell, which I've explained. Then the one also that compute for our test step. So remember, this is for training step, and this is for test step. Then the weight, we set our weight, initialize our weight again. Then this is the customized loop now. So we're inside the loop. So inside the loop, we calculate our epoch average here using the metric.mean. Then our test accuracy is set here. So in each value inside our training data set, we train with these steps, get the loss, and the loss average loss is calculated here. Also inside our test set, so we get the training test step here, the training step, and then our test accuracy will update the states, and then we can compute here. We can print all the results here. So when you do that, so you can see also it is very fast. Although we did not calculate time here, but if you test this with bigger model, you'll be able to see and that it runs faster than when you are not using mixed precision. So I've just shown you two for when you are using custom loop, training loop, and when you do not use custom training loop. So with custom training loop, you have to set your mixed precision, loss, scaling, all of that. Then you have to scale, you have to unscale back, unscale gradients and all that, with all the theoretical which we have explained before. So here, one thing you can do again is to optimize further. There's what we call the XLA compiler. So you can use the XLA compiler by adding this you add this to the environment variable, then you enable the JIT compiler on each of the top of custom loop that you have. That is, our custom loop exists between each of these functions. So what we need to do here is, first thing is to add that. Let's come here, then I can enable the mixed precision here. Remember, we don't get confused. The enablement we are doing here is for the XLA. So we enable it like this. Then let me run this as I've enabled that. So we are still under float 16. Then I can come here, then add the JIT to it as well, just to show you that you can add it in front of the function here, just in time. Also, you can add that here, just in time. And add that here. So then I can run this over again. Run this over again, then run this also over, and run this as well. Run this as well. Then here, so we can also run this as well. So it will make it faster. You can see, if you can see here, is enabling the JIT-XL compilation. This is TensorFlow, special TensorFlow compiler, which we run with using the JIT there. So you can also use this, and if you use this is combination of mixed precision and the XLA, so which give more optimization. So this is it on mixed precision. Then, so I'm about to round up. Just 2 more slides. Let me shut down this panel here. Then can leave. Also, can leave here. So so back from the demo. So there's another better way to do what we have done before. So in that other way, which to use now automatic mixed precision with our TensorFlow, is that you set this environment. Although we have seen how we can set this environment. So if you are working with graph base, what you need to include is just this enable mixed underscore precision underscore graph underscore rewrite. You use that to wrap your optimizer, and it is done. So you don't need to unscale, underscale, you don't need to do that. That's how automatic mixed precision is very easy to use. And if you are using Keras base as well, you can just do that as well. Enable underscore mixed precision graph rewrite to wrap your optimizer, and everything is done. It does the scaling and unscaling itself within. It does that within. So to show you that, I can just, because we can only do that with TensorFlow version 1. If you can see here, this is version 1 here, container. So I will run this again. So we won't waste time on this. Okay. I think I can come here, then let me have that. Okay, now I will run, this is our version 1 here. So in the version 1, this is what we've import TensorFlow. We have import our Keras, our layer, OS. Do you see we did not import mixed precision here? So what you can do here is that here I've set my environment for CUDA device because I want to use GPU. Then I set the environment here. So after setting the environment here, let me just run this. That is done. So you can see the version of the TensorFlow is 1.14 here for automatic mixed precision. So here we're getting our value here, loading the data from MNIST, then the train and the test data, then the input size, which is the shape of the input is 784. Then we have our 2 dense layer and the output layer. So here we care less whether our activation function is on float 32 or is on float 16. We don't need to bother about that. So I run that. So downloading, putting our download the data that we need. So this is the crucial part here. So we define our model here, the input and output. So then we load our optimizer. So after loading your optimizer, the next thing to do is to wrap the optimizer under TensorFlow.train .experimental. Then you wrap it with what? Enable mixed precision graph rewrite. So you wrap that against your optimizer. So once you do that, this is just a single line here. So which makes automatic mixed precision makes life easier. So you wrap that here, then you compile. This is the normal line to compile. You have your loss, your optimizer, your metrics that you want to use to compile. So let me run that cell. After running that cell, then we can initialize. When initialize, so initialization is done, then so we can now run our model as well. So you see, we don't need to do anything further here as well. So just run the model. You can see how the model runs. You see, it's even it's faster, a little bit faster, but we can't judge based on the little model we've done. It's 0. This is first one took 1 second, and other subsequent epoch. This number of steps just took 0 seconds, and you can see this is just mere microseconds. yeah, 6.6, why the other one took even more than that there. So this is just how to use automatic mixed precision. So how do we check with this TensorFlow one if we are not using automatic mixed precision? Or let's compare with when no automatic mixed precision is used or mixed precision is used. So if I clear the kernel, yeah, I clear, then I comment out this that is not used, is not enabled, and I'll also come here. This is the line here, and I comment this line out. Yeah. So now we are just running our normal TensorFlow with normal price. So we can see here. I run this slide. Okay. And also run this. So we don't actually need with initialization. We might not run that. We'll just run it. So, and then let's see how long it took with that. So you can see when you run it normally, this is the steps. It takes 1 second, 1 second, 14 microseconds, 1 second, 2 seconds. So this shows the efficacy. Imagine while you are running a bigger model, the scale up will be, the differences will be very glaring that you can easily see as compared to small model. This is just a small demo, I must say. So from here, so we are back here. So I've explained how to use the automatic mixed precision with TensorFlow. Rather, it also exists in PyTorch. So this is how you can do that in PyTorch. So you input from CUDA, your automatic mixed precision with Gradescaler. Then for optimization here, you AutoCast as well. You get your loss. Then also you scale the loss the backward. Then you also would get your scalar.step, and then you update the weight as well. So for more details, you can check more details here on how to do this, but I did not prepare for the PyTorch version as well. But if you check on this link, it is very, very explanatory. You can easily get how to do it very well. So thank you.